got here the control board from a dishwasher, and you can see there the control chip for the little low voltage switch mode has exploded. The top of it has come off, and I've got it here. That is an LNK, whatever that says, an LNK364PN, Power Integrations, little thing that's got all the bits you need to make a switch mode in it. You just join the feedback from the optocoupler, and then that pin by itself, the drain of the FET goes to the transformer, and got a switch mode. Unfortunately, we can't just glue that back on and expect it to work because the smoke has escaped from it. So we've got to find something else. So I was told by the person whose dishwasher this came from that they don't mind if it cannot be fixed because they'll just get a new dishwasher. I think we should have a go at fixing it at least. I did notice an interesting thing there. Some kind of dirt on the surface, and it looks like some tracking has occurred across there, which will be a mains voltage gap. Yeah, since that there's the main neutral, and that's the fused side of the phase. That's where the phase comes in. So that needs to be cleaned off. Otherwise, everything else looks in reasonable condition. That's the microcontroller there. This thing, don't know what that is. Doesn't matter. And the other IC, which is there, is the relay driver, ULN2003 standard Darlington driver thing, which drives these relays. The power supply here has got two outputs. One of them must be 12 volts, which drives these relays. Those are all 12 volt coil relays. And the other one, it's either going to be 5 or 3.3 volts, which is whatever this little microcontroller uses, and that will be the one that regulates. So there's a TL431 there, and some resistors. I haven't looked up the value of those, but they'll be creating a voltage divider across the adjust pin of the TL431, and that will set the voltage. That then triggers the optocoupler, which tells the switch mode control chip to stop switching when the voltage is reached, and it will oscillate on and off and maintain the voltage. Single-sided board, so they've used a lot of 0 ohm resistors to create jumper links over the pads. So I don't know why that's blown up. It could just be because it felt like it, or it could be because something's marginal and it only runs for 15 years and then just blows up, or it could be because something else has failed. So we should check some obvious things first before we continue. We'll look at the rectifier diodes. They should be conducting in this direction. 0.4 volts, 0.2, standard sort of Schottky diode stuff, and in the reverse they should be blocking, which it looks like it is. What that is charging up a capacitor on the board. We probably should change these capacitors because they would be exposed to some ripple over their life. Looks like both diodes are in good condition, or working condition. We could try checking for shorts on the transformer, but that might just show up as a short regardless because of the windings. And that shows up as open. Maybe that's a problem. It's possible that the transformer's blown. Oh no, I think it might have a thin layer of conformal coating on it, something on it, since it will be in a fairly damp environment in the dishwasher with heat and steam. So there's a resistance there. The output of the transformer, the secondary, that's the common, and then there's two windings. Oh, it's quite hard to get a contact. I need some sharp probes. I might have some better probes. Let's see what these reckon. Yeah, nothing. It's still not making a connection. I'm gonna push it really hard. There must be some tarnishing. It measures 0.1. But the thing is, the transformer's not going to have very many turns on it, so that is somewhat believable resistances there. Not sure about the primary though. 2 ohms. I think it might be a bit more than that. But I don't know. What I've done, we need to replace this chip, that's definitely known. But I don't have a chip of that part number. I've rummaged around on the lounge floor and I found a whole bunch of switch modes that all have a similar type of control IC with that leg out on its own. There's one in here. That one. There's one in this, which is like some sort of thermocouple isolator thing. There's one in there, surface mounted. There's this, which is a gruntier version, and the TO220 package. And there's this, which has got one. I think this is from a projector on there. And then I found this computer power supply, and that's got one in there for the standby power. But none of them match. They're all the same sort of thing, all power integrations, but they don't match. Let's check the resistance of the windings on this just as a comparison. 3.9 ohms, so the one on this board is somewhat believable, being a couple of ohms then. Maybe we could get a second opinion from this one. Maybe we should put this in frame as well. Oh, I don't even know what is the main coil on that one. I think it's that. That one looks like it's got an auxiliary winding. Yeah, I don't know. Anyway, so I want to change the capacitors. We've got to change the chip. Need to look up what kind of capacitors I've got. These two here are in parallel, which is interesting. They're different types. Not sure if they're reputable brands. They look like Panasonic capacitors, the black ones. Those Rubicons on the primary, those should be fine. We won't need to change those. That, whatever that green one is, it also looks Panasonic. It's got the M logo on it. So fairly decent capacitors. We'll just scrape away this gross stuff that's there. Don't know what that is. Something across a VDR. So I've made a chart that includes all of the different chips that I found in this collection here. The one we're trying to replace is this top one here, LNK364, and then I've listed all the other ones that I found down here, and then some specifications, pinouts, and the application circuits, and then I've ranked whether I think they're a good match or not. So some of them have not the same switching frequency, so those are red. These ones here are possibles. That's possibly more possible because it's got these legs you can bend into the right holes. I was thinking this would be the go, but the issue is it needs a primary side auxiliary winding there to power the feedback optocoupler, the transistor side, whereas the original there, you see it doesn't need any of that. It's all self-contained, makes it much more simple. So I've written that one off. Similarly these, because they take the same circuit. That one's no good because its power rating is so small, whereas the original was 9 watts. Similarly for that, and it's the wrong frequency. That's a Panasonic one, it's different. Frequency is probably close enough, but you can see there it also needs the auxiliary winding, so that's no good. So that brings us to this one. It has the right switching frequency, has enough power rating, doesn't need an auxiliary power supply on the primary. So I've marked that one green. The only thing that's different is, depending on if we can see them both at the same time, that one takes the BP, I think, so the bypass for the internal reference to ground there for that capacitor. So it powers the optocoupler through that and goes into the feedback pin. Whereas this one here is the other way around. The bypass / mode, I think, pin goes to a bypass capacitor to ground, but then the optocoupler comes out of that enable or undervoltage pin and then goes to ground. So it's a slightly different topology, and also the pinout is quite a bit different. I need to get these both on screen. I'll sort that out. So we've got the original one here. We got the most likely replacement one here, and you can see that sort of mirrored the drain pin there by itself and the pins on the opposite side, and then there's some 4 sources in that corner, and this one has the 4 sources down that side. So if I put the chip up the other way, like solder it to the bottom side of the board, so we've got that there arranged the same way as this, but we want to fit this. So if we turn it over, so we've got the drain there, that's now in the right position for that, and then we got these sources, so that will hook up to those 2, and then the other 2 can be just hot wired across to it. And then we've got the feedback and bypassing. Bypassing can just go across the top of the chip over to the source, which is what it wants according to this. Bypass down to source. And then the optocoupler, which will also come off source, so we can achieve that by shorting across that capacitor and moving it. And then the other side will be source, and then that side will be the going over to the right pin, the pin 2. But we'll probably have to swap the order of that. So maybe we'll pull that out of those pins, solder wires, insulated wires on it that come through the holes and then go to the relevant places. I think that's gonna be a go. I'll get the soldering iron sorted out, or up to speed, cranked up, whatever you want to do with it. I've created a diagram of how we should wire this up. I've also written down the capacitor values there so I can find some new ones. It will work pretty easily by soldering the new IC straight on from this side, and then we lift those two legs, then they solder up to there. And that track there, which is there from the optocoupler, can remain. We just solder it on to the others. That pin from the optocoupler, which is here, lifts, and we wire that onto this side, and we replace, or take that capacitor and we put it across the top there. That should be everything we need to do. So we'll start off with getting these old parts out. I don't have my proper desoldering tool with me right now, unfortunately, so we got to do it the old-fashioned way, which is this guy. Need a trash receptacle. I'm just going to put a little bit of fresh solder on these to start off with, just to make it a bit easier to wet the solder, have it melt properly. We'll see how we go. Should be fairly easy because this is a single-sided board. I think they're all good there. Yeah, that's quite good for one shot on each pin and out it comes. A little exploded IC. See, it's actually exploded the whole transistor there because it's on that drain leg. Interesting. Perhaps there is a problem. Maybe the transformer's pooped itself. We can't really tell. Well, maybe we should try measuring the resistance now that it's disconnected. Let's see what it says. 2.3 ohms. Yeah. I guess we really need to put a inductance measuring device on there to get a better idea. Okay, we're going to lift the optocoupler, although I could just scrape the track. That'll probably be easier. I'll just scrape through that track there to disconnect that. And we've got to watch those pads so we don't lift those pads off. This is single-sided stuff. Very easy to wreck the board by heating the pad and moving it. So we're going to take these caps out. How much do we need to do that? I don't know. I'll check if I've got some replacement caps. I should have some replacement caps. We can try measuring these ones to see if they're good or not. Everything's indecisive, isn't it? Let's just pull them out just for fun. It looks okay. It's not showing any like bulging or leaking around its little leggies. Just heating up both pins at the same time. Like that, and pulling them out. Since the legs aren't crimped over, does the caps look alright? We'll just open up these pad holes again so we can put back new capacitors, or put back these capacitors. Desolder braid there. That's good. That's ready for new caps. Let's try and find a component tester and we'll have a look at these capacitors, the old ones. Here's a cheap and cheerful component tester which might work. Let's have a look. This is supposed to be 220 mic. Might not be connected up properly. Oh, the battery might have gone flat. Ah, that's no good. That's not what we want, is it? It's hard to get the battery out. Alright, I'll look into this and also look for some new caps. Okay, I found a whole row of batteries. Sure you want to watch me try and find a better one. That was 7 point something volts, wasn't it? Another battery clippers. Let's try this green one, see what it reckons. 6.8, so that's worse. That one does nothing, okay, that's real bad. Pretty sure all of these batteries are wrecked. 6.8, that's no good. 7.1, more better. 7.3. Is that better? I can't remember the number. 7.6. I think that's our go there. Let's see if we can measure any of these caps. Be easier to hold them onto that part. Okay, what we got there, 640. So that's probably good. Says the ESR 0.03, 420. Yes, that might be a bit pooped. And we got this one, 330 mic, 320. So that's probably okay. And this last one is 220. Bend the legs again. 217 from a 220. Yeah, I'll see what I can do for replacing caps. I think I found some suitable replacement caps here. Got a 470 mic 25 volt. That's going to replace the 470 16. We've got a 330 16. That's going to replace the 330 16. Got a 220 mic 25. So that's going to replace the 220 mic 10 volt. And we've got 1000 mic 25 volts, so that's going to replace the 680 mic 25 volt. That'll be fine because that's across the relays, just to stop the inrush of the relays from sagging the power supply down too much. Fits too, nice. So the next one, they put weird designators on this. They've used E rather than C for the capacitors. So E9, that was the 330-16. These are just left over from other repair projects. That's E9, isn't it? 330-16. Nice, another one that fits the footprint. Then we've got the 220 mic, that's E5. These two are in parallel anyway. E5 and E3. E3 is the 16 volt 470. These are all good capacitors. Made sure to buy good capacitors. So that's that one there. Presumably that's not too tall. Well, it's not taller than that relay, so it'll be fine. Yeah, footprint for that one's a little bit wonky, but not quite the right pitch, but that doesn't matter. Let's solder these in. That's good. Just check again, make sure they're all around the right way. Very important that they're around the right way. Good, so we'll cut the legs off. And save those because we can use them for links. Now we've got to get, I didn't get the little chippy out. A new little controller chip. So this is from an HP computer. It's a special type of power supply where they only output 12 volts. This is, and a little bit of negative 12. 12 volt standby 1.3 amps. That's the power supply we're stealing, the one that's always on. And then it's got two other 12 volt rails, 16 amp, 14 amp, and a minus 12 volt one. I think there's only one rail actually in there. It just comes out as two, but there's individual shunts on them. You can see the little Kelvin connected ground and sensor across those shunts. So there's two outputs independently measured, but it just comes from one rail. I think there's an inductor across there, and then there's the rectifiers. Yeah, there's that inductor, pretty thick windings there. Some pi filter type thing, and then there's diodes. The rectifier, active PFC, it uses that choke there. Maybe, no, there's the PFC choke. That there might be a, I don't know, is that a CT? I think so, that might be some weird thing. I think it's an inductor. Yeah, there's the little auxiliary power supply transformer, the standby supplier. That will be a pulse transformer for driving the primary FETs. Okay, we're going to get this chip out, that's what we come here for. So I've got to desolder this. That's when we could have benefited from the proper desoldering tool, but we just do the same approach as before, re-wet it with some new solder. This is on quite a large pad area for heat sinking. And it didn't work. It flowed back on straight away. That's good. Sucking two legs at a time there. Yeah, so you try and seal the soldering iron against this tip, so you end up burning these down pretty fast, but you can get replacements. But I find that's the best way to actually be applying heat as you're sucking them, rather than heating it, hoping it doesn't cool down before you get around to sucking it. which I never found very effective. There's some glue on this so it won't just fall out. Oh, it just sort of flakes away. Need some grabby things without destroying it. Okay, so we liberated our new control IC. And that power supply, it's a shame we wrecked that power supply, but too bad. Yeah, so what they've done is put some glue around this leg to stop tracking issues that you can have when there's high voltages, especially high voltages at high frequencies. Oh, we've got to cut the track there, so let's do that before we get any further, otherwise we're going to have big issues later on. So that is now properly isolated. Now we can put in our new chippy, this guy. But we've got to do some things according to this. We've got to insulate these legs, so we've got to try and bend those up without snapping them off. Maybe we put a bit of tape down. Oh, that's dodgy. So close to snapping off. Yeah, don't do that. Put a bit of tape down so that stays fairly insulated. So we don't have to insulate it from much voltage because they're all on the low side. And the only one we've got to worry about is that drain pin, which is already by itself, so that's fairly... We'll just need to get that cap out because we want to reuse that. Is that a good idea to reuse that cap? If we cut another track, it's already going to that cap there, it's already connected to the source pin, so we just need to cut another one there and then we can jumper it over. So we don't actually need to remove it, which is good because that would be pretty annoying to remove the surface mount cap without destroying it. It's possible, but it's just another risky maneuver that we rather not need to do. So you're going to cut another track. Just separates that other pin there off. Cut a little section of that track out. Pick it away. That's now gone. Which means now that can just go down completely. And that one in there. Solder it up a bit. I'm going to cut off. I should zoom in this way a little bit. That's already zoomed in. I'm going to cut that leg off so that it doesn't get too close to those other things. Hopefully we can solder to those. Hopefully they're not too tarnished because it's up in the bit that you don't normally solder onto. Right, I'm going to solder this in now. And then that's going to be the end of it because we won't be able to move it after that. I can't get in there with the desoldering tool. Now we've got to put one of those legs that we saved before across here to join all of those to the, whatever it's called, source. There we go, that's nice. So that makes a nice little heatsinky thing. Just bend that other end back down. Just adds to the amount of heat sinking it's going to get. Good. So that's nicely connected up there. And it's nowhere near those bits that we touched. Now we're going to get a little bit of wire. I'm going to create a little cable. Oh, a bit of wire. 2 bits of wire. Tin the ends. We're going to make 2 links. One goes from that cap, that cap up to that pin, and then the other one's got to go from that top pin there, pin 1, down to the opto. I'll do the longer one first, to the opto, pin 1, up there. Trim this down. And just make sure we can solder onto those pins. Good. Okay, that's coming from pin 1. Nice join onto there, down to the other pin of the opto. And it's not quite long enough. And we'll turn around slightly. And now make another little bit of wire that comes from the other pin and goes to the cap. Now solder that on there. Bring it around onto the other cap pin. Okay, I think we're ready for a smoke test. Well, not quite yet. I'm going to look over this very carefully and then we'll try turning it on. Now we should also solder up some test points so we can measure the voltages. Probably shouldn't have cut those leggies off the capacitors then, should we? So we could have used those to take a measurement when we power it up. I'll check this and tidy it up, and then if it's all good, we'll give it a go and see if it works. Checked it all. Pretty sure everything's good. Cleaned it a bit. So I've checked it. I've added these legs back so that we can measure the voltages. And I've got here standard issue blast shield and mains cable with alligator clips on it. What I'm going to do is change the fuse. Yes, I remember. What I did was I measured all the other diodes to make sure that there's nothing else gone bad, because there's a possibility the input rectifier would have shorted. Although if it had, it would have blown those. So I don't think that's a problem. Or there's the like flyback energy capturing snubber thing. That diode's fine. And what I'm going to do is replace the fuse. It's this fuse here, the regular one. Well, it's only 3 amps. Okay. Well, I'll just put a 1 amp. I think this here is a 1 amp fuse. Yeah, I'll just put a 1 amp fuse in while we test it, just in case something goes wrong. Well, yeah, in case the smoke tries to escape. So I'm going to got these leads here from the multimeter. We're just going to measure one at a time because I can't be bothered getting out another meter at this point in time. So the common's that. I have these coming over from the low voltage side. The common is that one. The regulated supply, which we'll measure first, is that one. And then the other 12 volt supply we'll measure is that one. Then we'll hook up our AC neutral. This is not plugged in at the moment. And our AC live, which goes onto here, which goes through the fuse, then onto there, which goes into the rectifier and through the circuit. There's also that. I didn't check that. That is possibly a fusible resistor. Maybe we should check that. That could have blown. Check it to here, so we don't have to worry about breaking through the conformal kit stuff. Check it to here. 10 ohms. Okay, so that's still fine. The multimeter back onto volts. Hook that up. That's hooked up. That's all hooked up. That's on the positive of the regulated supply. That's on a negative terminal. That's on the positive of the other supply. Put that there. Put our regulation blast shield over it. And then we'll just juice it up. And get this meter into view so we can see. Hopefully it works and doesn't just... I kind of want to watch that in case it does explode. So let's have it up that way in case it blows up. That way we can actually see what the deal is. Ready? Go. Oh, look at that. It beeps. And it's exactly 5 volts. And I heard the relays clicking. Let's check the other rail, which I believe is 12. Close enough, since it's unregulated. Oh yeah, it goes down to 12 when the relays are on. Okay, we can shut that up. It looks like it was a success, although it's going to take time to tell whether we've got something lurking about to explode. So unplug that, because we don't want dodgy things happening. Got to put back the original fuse. We should measure that before touching it, but we got that issue that there's that thick conformal coating stuff on there. Or not, there's that thin conformal coating stuff that doesn't let the probes through very easily. So presumably it's beeping because whatever stuff joins onto this board is not there and it can tell. So it's unhappy about something. It might be a thermistor or something like that to measure temperatures. Or some other feedback thing. I want to leave my low value fuse in there and have the thing poop itself a short time later because the fuse has become marginal. We'll put back this original one, which was 3 amps. Put this little cover on. Okay. Oh, I've got to get rid of those legs. So I think that was a bodge well done. I was wondering if I should put a little bit of glue on that. Probably doesn't need it because it's got almost all its pins are holding it down. So I think it's probably fine. Good as new. See you next time. Just as an extra bonus bit, let's try to take a look at the chip. Or the explosion site in the chip. So there's a leg coming in, looks a bit rusty. But there's where it popped. And it looks like it's a big crater, seeing how the focus works. The depth of field is so tiny on this lens, but yeah, it seems to have exploded itself a huge crater and just left those connections just dangling there. Is that the rest of the die? Could be, I'm not sure. But yeah, pretty good explosion. Now if we look at the piece that got exploded out, you can see there a protrusion on it, which is what went deep down into that hole. Nice. Bang. Fixed now.